We are used to seeing weather like this: flat maps, contour lines, some color fills maybe, troughs, ridges, and the upper level flow regime in general. But this is the exact same 500 millibar field in 3D. And once you look at it like this, troughs and ridges stop being just shapes on a chart. A trough is not really just a U shape in the 500 millibar height field. A ridge is not only just an inverted U shape in a 500 millibar height field. In 3D, however, they begin to look much more like valleys and hills in the atmosphere itself. Hey everybody, welcome to the weather breakdown. If you watch one of my earlier videos, you may remember that we've already explained how jet streams and jet streaks form, how the geostrophic balance, the horizontal pressure gradient force, and the Coriolis force act to shape the upper level flow pattern. In this video, we're going to delve a little bit deeper into it and add something that is usually missing. It will allow us to look at the atmosphere and how these forces act upon the structure of the atmosphere itself. Once you stop seeing upper air charts as a flat contour pattern and start seeing them as real atmospheric structure, a lot of meteorology starts making much more physical sense. On a normal 500 millibar chart, a trough looks like a bend in the contour lines. A ridge looks like another bend, just in the opposite direction. But here, that same trough becomes more like a valley carved into the upper level millibar surface. And that same ridge becomes more like a hill or an elevated bulge in the height field. So the big question is, why does the 500 millibar surface have this shape at all? Why is it higher in some places and lower in others? The answer lies in the hypsometric equation. In simple terms, the hypsometric equation tells us that the thickness of a layer is directly proportional to the average temperature of that layer. Warm air expands and cold air is denser and more compressed. So if you compare a warm atmospheric column to a cold one, the warmer column will be thicker. This means that the vertical distance between the pressure level is greater in warmer air and smaller in colder air, and that has a direct consequence for the 500 millibar level. Over warmer air, the 500 millibar surface is found higher up. Over colder air, it's found lower down. So the 500 millibar surface does not sit at one identical altitude everywhere. Its height changes across space depending on the thermal structure and the atmosphere below it. That means what we are looking at here is not arbitrary at all. This surface has shape because the atmosphere does not have the same thickness everywhere. Warm regions lift the 500 millibar surface higher, cold regions keep it lower. And when these warm and cold regions sit next together across a horizontal distance, the 500 millibar surface begins to slope. That is the key idea. Temperature gradients create thickness gradients, and thickness gradients create height gradients aloft. And suddenly, this 3D view becomes much more than just a cool visual. It becomes a way of actually seeing the consequence of the thermal structure of the atmosphere. This is exactly what those contour lines on a 2D 500 millibar chart are showing you. They are the flat signature of a pressure surface whose geopotential height changes from place to place. But when you lift that field into 3D, it becomes much easier to understand what a trough or a ridge really is. One of the things I really like about doing this inside the Chase Buddy is that I can move between the familiar 2D chart and this 3D structure instantly. That makes it much easier to connect the classical meteorological view to the actual atmospheric geometry behind it. Now, when the 500 millibar surface slopes through space, an important consequence appears. pressure surfaces are no longer parallel to geometric height surfaces. And that means that if you compare two locations at the same height, their pressure is not necessarily the same. And it's that what creates a horizontal pressure gradient force. And once that horizontal pressure gradient force exists, the atmosphere responds. Air begins to accelerate from higher pressure to lower pressure. But because the Earth rotates, that motion is deflected by the Coriolis force. And as the air accelerates, the Coriolis force strengthens until it comes into near balance with the horizontal pressure gradient force. That balance is called the geostrophic balance. It is the wind created by the balance between the Coriolis force and the horizontal pressure gradient force. And once that happens, the wind flows largely parallel to the height contours rather than straight across them. And from that, you can immediately understand where the 500 millibar jet will be faster. If the gradient is higher, then the wind will be faster. If the gradient is weaker, then the wind will also be weaker. They are absolutely connected. Now, this is the kind of visualization that I like in the Chase Buddy and why it's so exciting to work with. And if you want to explore these views yourself, the Chase Buddy is a free app. You can download it on iOS and Android. And if you like these meteorological deep dives, feel free to drop a comment in the comment section, say what you thought about the video. Also, don't forget to subscribe because this video is actually number one in a three-part video series around looking at meteorology from a 3D perspective. Thanks for watching, guys, and see you later.